In this video, we're studying a new topic of integration and applications of integrations in the field of further calculus. So recall integration rules from mathematical methods that you will have done in the past. So for all of these functions f of x, we have an antiderivative, capital F of x, which is the integral of f of x with respect to x. So for ax to the n, we have ax to the n plus 1 over n plus 1, and then of course our constant of integration. As when we differentiate, I should say, as when we differentiate a curve, we don't know what its sort of vertical shift is. We have to accommodate for that when we do an anti-differentiation or when we integrate it. So we add that c to sort of accommodate for that fact that we don't know where it is in the y direction. We just know what its slope is. So moving on, we've got e to the kx is e to the kx on k. Sine of kx is negative cos of kx on k. Cos of kx is positive sine kx on k. And then secant squared of kx is tan of kx on k. So looking at the chain rule for differentiation, we can write dy dx in terms of du and du and du dx. So dy dx is equal to dy du times du dx. So if we call dy du a function of u, we can see that a differentiation can always be represented as f of u times some derivative of u with respect to x. So that means the integral of f of u du dx dx is just integral of f of u du. And what that means is if we can write du dx, we can substitute it in, so those dx's, they kind of cancel each other out, I guess you could say. It's a bit more complicated than that, but all you're left with is a function in terms of u and anti-differentiating with respect to u. So that's something that is sometimes easier than doing y with respect to x. Let's take a look at that now. So for part A, we have the integral of 5x squared times the square root of x cubed minus 1 dx. Now that 5x squared blah 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 is referred to as the integrand. It's what's inside the integral. So when looking at this integrand, we can see that we have a function under the radical sign that when differentiated gives us the product. It gives us an x squared term. So if we let u equal x cubed take 1, we can see differentiating that with respect to x gives us 3x squared, which is the same order of x as our coefficient. So 5x squared compared to 3x squared. So what we can do is we have this dx up here, and we have a dx here, and those are the same dx. It's the same differentiation with respect to x. So if we rearrange this function to make dx the subject, we get that dx is just du over 3x squared. So if we substitute that back in and replace our x cubed take 1 term with u, we get the following. And so what we can see here is that x squared term that we have at the front cancels out with our change in variable. So we've changed from the variable x to the variable u, and by doing that, we've eliminated the fact that there is a product of functions here. We turn it to be just a single function. So these x squareds cancel, and we're just left with 5/3 taken out the front as a constant of integration, and we're left with square root of u du, and that of course is then just going to be two-thirds times our 5/3 times u to the 3 halves plus our constant of integration. So we get 10 ninths times x cubed take 1 to the power of 3 halves plus c. And that's our final answer for that one. Okay. Part B, I'm going to write it down here so that we've got it. So integral Okay, so for part B, we see we've got sine of 2x and e to the power of cos 2x. And we can see that sine of 2x is almost the derivative of the power of e. So what we're going to do in this case is let u equal e to the cos 2x, so that when we differentiate it, we also have e. So we're going to get negative sine of 2x times e to the cosine 2x. So what we're going to do now is replace e to the cosine 2x with u, and we're going to rearrange to make x the subject. Oh, sorry, I'm missing a coefficient of 2 in this derivative, because we also have to take the derivative of what's inside of the sine term. So that's going to be 2 sine x. So negative 2u sine 2x under du. So substituting that into our integrand, we get sine of 2x times u times du on negative 2u sine of 2x. And what we can see here is that we have a u sine of 2x term here and a u sine of 2x term here. So those two cancel out. And this is the same as just finding the integral of negative a half du, which is just negative a half e to the cosine 2x plus c. So it's negative a half u plus c, and then I substitute in my value of u. Lastly, part C, we've got x squared 3x take 1 integrated with respect to x. So for this one, we want to let u equal the entire square root here. So if we let u equal 3x take 1, what that then gives us is a derivative of 3 on 2 square root of 3x take 1. So what we can then do now is this u is in terms of a square root of x. We want to rearrange that so that we know how 3x is defined. So rearranging this u, we get u squared plus 1 on 3 is equal to x. So we've got u squared plus 1 on 3 is equal to x, and that means we can substitute in for x squared. So we also have that dx is equal to du times 2u, because that's what's on the denominator here, 2 times u, over 3. So that's just rearranging this to make dx the subject. So now substituting that all into our integrand, we get u squared plus 1 squared on 9 being multiplied by u squared du, and then we also have a factor of 2/3 out the front. So that u squared is coming from the u of our square root 3x take 1 and the u that is in our dx term there. So we get two lots of u, that's u squared, and then we get that 2/3 from this dx symbol here. So carrying on over to the right here, we can take out that factor of a ninth. We get 2 on 27 integral of u squared plus 1 expanded gives us u to the 4 plus 2u squared plus 1. That's being multiplied by u squared. We get that's in terms of u. And so expanding this out, we get 2 over 27 integral of u to the 6 plus 2u to the 4 plus u squared du. Now these are just a polynomial, so we can do this. That gives us 2/27 u to the 7 on 7 plus 2u to the 5 on 5 plus u to the 3 on 3. And we can take out a factor here of u squared, which we know is, of u cubed. So that gives us 2u cubed on 27. We get u to the 4 on 7 plus 2u squared on 5 plus 1 on 3 plus c. So what we can see here is that inside of our brackets we've got u to the 4 and u to the 2, and because our original u was square root of 3x take 1, this is actually just a polynomial. So it takes a little bit of work, but this then becomes 15 3x take 1 squared plus 42 3x take 1 plus 35, and that's all being multiplied by 2u cubed over 2,835. So all I've done there is multiply each of these three terms by 7, by 5, and by 3 all at once, and taken that out the front. So we eliminate the fraction, and what that ends up being is 2 times 3x take 1 to the 3 halves, all on 2835, times by expanding and grouping like terms. We'll get 135x squared plus 36x plus 8 plus c. All right. So that's a lot of work there. We can see immediately we had to identify how can we take this product of two functions and turn it into something that is not a product of functions, something that just has a u term and a du. So we know that we can quite easily integrate this polynomial. So how do we get to there? Well, we need to know what x squared is, and we need to know what root 3x take 1 can be represented as. Okay, so moving on from indefinite integrals to definite integrals, we need to consider what happens to our bounds when we change our variables. So we're starting with t now instead of x. So we're going to let u equal, well, which of these two is going to help me out? If I take this denominator, I know that the derivative of that is going to, or at least just the t squared plus 4 is going to be t. So let's see what we can do with that. So we get du on dt is equal to 2t. This is looking really promising. So we make dt the subject. We get that dt is just du on 2t. So now that we have dt and we have our function in terms of u, let's check out what our integrand becomes. But first thing to note, these bands are in terms of t, but if we're integrating with respect to u, we need to know what those bands are in respect to u. So let's do our u transformation. So this becomes t on square root of u times du on 2t. So our t's cancel. So our t's cancel, and we're left with the integral of something, sorry, from something to something is du on 2 root u, but we need to find out what are these bounds. So when t equals square root of 5, what does u equal? Well, that's going to be square root of 5 squared, which is 5, plus 4 is equal to 9. So we know our upper bound is u is equal to 9. Our lower bound becomes u equals 0 plus 4, which is just going to be u equals 4. So computing this integral now, we get the integral, sorry, I don't need to do that now. We get that 1/2 times our coefficient of 2u to the half, and that is from u equals 4 to u equals 9. So we get root 9 take root 4, which is just 3 take 2, which is equal to 1. So we find that the original problem we were asked, which is t over square root t squared plus 4 dt, is equal to 1. So we can see there we identified the issue. We needed to find a way to stop it from being a quotient of two functions. The easiest way to do that was to get dt in terms of du and then having t on the denominator. So when we do that variable transformation, the quotient of functions in terms of t cancel out, and we're just left with that du on 2 root u. That's all for this video. Thank you very much.